13, that is मैग्नेटिक इफेक्ट्स ऑफ इलेक्ट्रिक करंट का रीडिंग, जिसका हम सेकेंड पार्ट देखने वाले हैं. सो लेट्स सी. मैग्नेटिक फील्ड ड्यू टू अ करंट कैरिंग कंडक्टर. In activity 13.1, we have seen that an electric current through a metallic conductor produces a magnetic field around it. In order to find the direction of the field produced, let us repeat the activity in the following way. Activity 13.4. Take a long straight copper wire, 2 or 3 cells of 1.5 volt each and a plug key. Connect all of them in a series as shown in figure 13.5a. Place the straight wire parallel to and over a compass needle. Plug the key in the circuit. Observe the direction of deflection of the north pole of the needle. If the current flows from north to south as shown in figure 13.5a, the north pole of the compass needle would move towards the east. Replace the cell connection in the circuit as shown in figure 13.5b. This would result in the change of the direction of current through the copper wire, that is from south to north. Observe the change in the direction of deflection of needle. You will see that now the needle moves in opposite direction, that is towards the west. Figure 13.5b. It means that the direction of magnetic field produced by the electric current is also reversed. Magnetic field due to a current through a straight conductor. What determines the pattern of magnetic field generated by a current through a conductor? Does the pattern depend on the shape of the conductor? We shall investigate this with an activity. We shall first consider the pattern of magnetic field around a straight conductor carrying current. Activity 13.5. Take a battery of 12 volt, a variable resistor or a rheostat, an ammeter of 0 to 5 ampere, a plug key and a long straight thick copper wire. Insert the thick wire through a center normal to the plane of rectangular cardboard. Take care that the cardboard is fixed and does not slide up or down. Connect the copper wire vertically between the points X and Y as shown in figure 13.6a. In series with a battery, a plug and a key. Sprinkle some iron fillings uniformly on the cardboard. You may use a salt sprinkle for this purpose. Keep the variable of a rheostat at a fixed position and note the current through the ammeter. Close the key so that the current flows through the wire. Ensure that the copper wire placed between the points X and Y remains vertically straight. Gently tap the cardboard a few times. Observe the pattern of iron fillings. You would find that the iron fillings align themselves, showing a pattern of concentric circle around the copper wire. Figure 13.6. What do this concentric circle represent? This represents the magnetic field lines. They represent the magnetic field lines. How can the direction of magnetic field be found? Place a compass at point say P over a circle. Observe the direction of needle. The direction of north pole of a compass needle would give the direction of a field lines produced by the electric current through the straight wire at point P. Show the direction by an arrow. Does the direction of magnetic field lines get reversed if the direction of current through the straight copper wire is reversed? Check it. What happens to the deflection of compass needle placed at the given point if the current in the copper wire is changed? To see this, vary the current in the wire. We find that the deflection in the needle also changes. In fact, if the current is increased, the deflection also increases. It indicates that the magnitude of magnetic field produced at a given point increases as the current through the wire increases. What happens to the deflection of needle if the compass is moved from copper wire but the current through the wire remains the same? To see this, now place the compass at further point from the conducting wire, say at point Q. What change do you observe? We see that the deflection in the needle decreases. Thus, the magnetic field produced by the given current in the conductor decreases as the distance from it increases. From figure 13.6, it can be noticed that the concentric circles representing the magnetic field around a current carrying straight wire becomes larger and larger as we move away from it. Right hand thumb rule. Right hand thumb rule. A convenient way of finding the direction of magnetic field associated with the current carrying conductor is the following way. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then your finger will wrap around the conductor in the direction of field lines of the magnetic field as shown in figure 13.7. This is known as the right hand thumb rule. Figure 13.1. Okay, right hand thumb rule. This rule is also called Maxwell corkscrew rule. If we consider ourselves driving a corkscrew in the direction of current, then the direction of corkscrew is the direction of magnetic field. Example 13.1. A current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below and at a point directly above it? The current is in east to west direction. Applying the right hand thumb rule, we get that the direction of magnetic field at the point below the wire is from north to south. The direction of magnetic field at a point directly above the wire is from south to north. From right hand thumb rule. Question. Draw magnetic field lines around a bar magnet. List the properties of magnetic lines of force. Why don't two magnetic lines of force inserted each other? So the answer of these questions are given in previous points. So now we have completed our 13.2.2 concept. Now in next video we will start our 2.3. So thank you.